Page 95 is where we're at, and we're just going to review very quickly about Rutherfords Experiment. You see on page 95, figure 3.6, there is a diagram there showing Rutherfords Experiment. And again, let's see. It's going to be troublesome. I'm not going to keep going back and forth with the recording, so I apologize if we do end up losing it. My system shut down on me this morning, and now Windows is giving me all these recommendations to fix it, which is clogging it up again. So what Rutherford did, you can see it on page 95, figure 3.6, that radioactive isotope, what he did, I know Tyler didn't go into a lot of detail on this, but let's say we have this piece of radioactive stuff, right, and it's emitting alpha particles. So what Rutherford did is he put this inside of a box. See, I had Mr. Parker's art class, so I tried to draw three-dimensional. Okay? So he has this piece of radioactive material inside of a box, and then to make the gun that shoots them, all he does is make a little pinhole. So we're going to go in the negative, okay? So let's pretend this is a hole in the box. So while this thing is emitting alphas in all different directions, the only ones that are able to come out of the box, this is a lead box, so it's protecting everything from the radioactivity, but the only alpha particles that can come out are the ones that shoot out through that hole. Okay? So they're all shooting out through that hole in that direction. And then the distance over here till you get to the target, the gold foil, and the fluorescent material that's in a semicircle around it. Now in the middle here, there's another, just think of it as a piece of material on a little stand, okay? And that also has a pinhole in it. So what's happening here is of all this general radiation, only that which is going in this direction is allowed through. And then as it's traveling, it may be scattering a little bit, right? It might, like a flashlight beam, it may be scattering a little bit, but there's another focus point which only lets those things which are at that point through. So when he makes the alpha particle gun, that's all it really is. Alpha particles are shooting through that pinhole, and of those that make it through the pinhole, they diverge slightly, but when they hit the second target, it has a pinhole in it. So everything but those that are in the middle are stopped, and those go straight into this point. And that's when he sees that some things are deflecting. Most are going straight through. Some are curving way back, and some are almost coming all the way back. Now this target area here goes all the way around and just has an opening like that. So he's monitoring all those different impact points. And by assessing this experiment and experimental results, that's what we came up with the nuclear model. We said, you know what, plum pudding just simply isn't going to work. And if you, for all these different paths, this mess that I have over here, that's depicted on figure 3.8 on page 97. The alphas are coming in, they are coming up to the gold foil. I'll say hitting the gold foil, but remember, nothing physically ever really touches anything physically. But the idea is, as they come through, most of them go through, straight through. They're not affected in any way. Some are deflected, some are radically deflected. And so how does he explain that? And it didn't explain everything, but it explained most of what he saw is coming up with the idea of a nuclear atom. We say the nuclear atom, it's as opposed to the plum pudding atom, which was opposed to Dalton's indivisible atom. So remember how Tyler did that on the video. He said the billiard balls are Dalton's, atoms are circles, spheres that can't be broken. Then plum pudding said at least the electrons can separate out, so those have to be like blueberries in the muffin. It's actually plums in the pudding. And then because of Rutherford, we came up with the nuclear model where we say that there's a nucleus. The nucleus contains particles, and around the nucleus are electrons. What exactly was in that nucleus? Here we discovered protons, and then after protons was the discovery of the neutrons. And so we come up with what we have now as a more complete nuclear model. It's at this point in the discussion that the authors take us into a discussion on light. And it might sound like it's a little bit, or seem like it's a little bit of a distraction, but recognize when we're looking at these particles, and we're looking at how they impact and they fluoresce on the target, and some other aspects of elements we're going to look at, that we start talking about, I can see the light hitting, I can see light, I can see these certain things because of the light that they emit. And so what is light? That, my friends, and I do consider you friends, is a real conundrum. It's a real difficulty. What is light? Light, if you think about it, light is one of those things that we said previously is not really part of the discussion of chemistry. We're going to use it in chemistry, but in its purest form, it's not actually chemistry. Why not? What is the study of chemistry the study of? Remember from the very first day? Chemistry is the study of those things which have matter and take up volume. Does light have matter? That's a good question. Does light take up volume? The most common thinking is that no, light does not have matter, and light does not take up volume. If it had matter, it would take up volume. But then we're faced with the nature of light, and if you see on bottom of 98, this definition, it's in blue, so you're expected to know this. The nature of light. The particle-wave duality theory. I'll read it and then we'll talk about it for just a moment. The wave-particle duality theory. The theory that light sometimes behaves as a particle and sometimes behaves as a wave. Put another way, if you design an experiment to prove that light is a wave, you will prove it's a wave. And if you design an experiment to prove that light is actually a particle, you will prove that it's a particle. The question is, how can it be both simultaneously? How can light be both a wave and a particle, since the characteristics are very different? We can't really understand how something can be both simultaneously. If we were to say sometimes light is a wave and sometimes light is a particle, okay, which is it at this moment, like a certain sample of light? But any given light is both a particle and a wave, depending upon how you view it, how you experiment with it, how you interact with it. So I want you to be aware of that on a question. If it says, is light a particle or a wave, the answer is yes. And I use this analogy theologically when we talk about some things that are real conundrums for us theologically as well. As a person, before I was willing to become a pastor, I had to be able to, in my own mind, reconcile my inability to answer certain questions. Before I became a pastor, I had to be willing to say to someone who came to me with a deep theological question that was pressing on them, Pastor John, what is this? What's the answer to this? To be able to look at them and say, I don't know. Okay? There's a lot of pressure for pastors to always have an answer for every question that comes up. But there are certain things that we frankly don't know the answer to, and sometimes we make up the answers to, and we look at Scripture and we think we know what Scripture should have included but forgot to put in there. What did God forget to put in the Bible for us that we actually need? And yet we're convicted when Scripture says everything we need for life and godliness is in the Scriptures, right? Everything we need to know is there, so don't press too far if just because you have a piece of information, a question that you feel you have to have answered, that it's not answered in the Bible. Okay, do you really need to have that question answered? Do you need to maybe reconsider that question? One of the most complex, difficult to understand, and longest lasting dilemmas in the church, in theology, is the whole issue of sovereignty and free will. Do you believe that God is absolutely sovereign, that God stands outside of time, that God doesn't have time passing like we have time passing, but that he's above time and looks into time, and he's outside of time? The very fact that Christ came, part of the humiliation of Christ becoming a human, but he also at that point had to step into time. And that for all eternity, for future, Christ is embodied and chronologically in time. For God the Son, there is a yesterday and a today and a tomorrow. For God the Father and God the Spirit, those things don't really exist. There's no such thing as, what's his name? The I Am, the eternal present tense being. No past, no future, just pure being. Christ stepped into time into flesh and had a yesterday, today, and tomorrow, and for all eternity will have a yesterday, today, and tomorrow, so that the humiliation of Christ to become our sacrifice was an eternal humiliation in certain aspects. So this kind of an overarching, powerful, sovereign God who has nobody that tells him what he has to do other than his own character tells him what he's going to do. And his character we call holiness, and those things that violate his character we call sin. At the same time, we see in Scripture that individuals are accountable for what they do. That we're not just simply robots or automatons, that we do have determination. We can make choices, and we do become accountable for the choices we make. And how does a person who has the freedom to make choices yet have a fallen nature, who are predisposed to choose poorly, to choose in opposition to God and anarchy against God, how can that individual truly have free will? And how can that person be held accountable for things that are beyond their control? Push as hard as you want, but I believe ultimately at the end, don't know. Ultimately at the end, it's a duality. It's a dual reality. That God is sovereign, man is accountable. The choices we make are real, and we bear the responsibility for the choices we make, though we are fundamentally flawed and disposed to make poor choices every time. Okay. So theologically, that's one way to look at it. Now, if you understand that theologically, that's what we're talking about with light. Is light a particle? Yes, it is. Is light a wave? Yes, it is. How can it be both at the same time? I don't have a clue. Scientists don't have a clue. This has been a problem, a conundrum to think about for a long time. I'm not saying scientists don't have a clue. There's a lot of theories about it. But nothing we come back and say, this is the prevailing model. This is what we all believe. Okay? So for this class, we're going to go with the duality theory that says that light is both a particle and a wave. And as they say on the bottom of 98, if you don't understand this theory, don't worry. Scientists don't understand how light can be both a particle and a wave. But we're forced to believe it because that's what the data indicates. So for those that think that science is the way to go because they have all the answers, the answer to that question falls to philosophy, not to science. But we can look at light as both a particle and a wave. And so rather than looking at it as one way, we now have to consider both ways. Speaking also, is light part of chemistry? If chemistry are things that have volume and mass, we do know, for example, that light can have momentum. And there's such a thing as a solar sail out in space. A sail that uses light that hits it to push a spacecraft. Well, in order for it to be pushed, something has to be impacting it with momentum. And for something to be impacting it with momentum, it has to have mass. And if light is what is pushing it, that would mean light has mass. So now we're stuck with something that has mass but may not have volume. Or does it? Again, light has a lot of problems for us, and that's why light is generally considered primarily in physics, because most of the way we understand light is mathematical. Okay. On page 99, figure 3.9, we'll get some very basic understandings of waves. This applies to all waves, but we're going to use it in the discussion of light. Talking about a wave, and this is going to be imperfect drawing, but I'm trying to replicate what's in the book. So this should be very symmetrical and very consistent, which I know it's not because it's very difficult to draw. But there's a wave. Think about a wave. Just think about the beach, okay? Not right at the beach. Let's go out maybe a couple hundred yards off the beach and see those rolling forms that are in the water as they seem to be moving towards the beach line before they start to crest and break. You've got the deeper ocean, the larger, longer waves, and as they get closer and closer to shore, they get closer and closer together. But this basic idea that light is like a wave, it moves through a medium. That's another thing. With sound, you need a medium. You need air for the energy. When I clap my hands, when I do this, what you're hearing is, as I bring my hands together, the energy from this is going out from my hand, but it's hitting the air that's right next to it, and it's actually the air moving and undulating that brings the sound to your ears. What's impacting your eardrums is a movement of air that was caused by the movement of my hands and the bringing of my hands together. So when I do this, I'm basically forcing air in your direction. And when it hits your eardrum, you hear not my hands, but you hear the energy from my hands that's been passed along through the air. That's why in space there is no noise. All these great Star Wars battles or whatever you want to think about, all the big explosions in space, they would be silent because there's nothing for the sound waves to propagate through to come to you to hear them. However, for light, we can see light. In fact, stars, sun. So we have here a wave that's propagating through a vacuum. How does that work? Most scientists say at that point we're talking about the particle nature of light, not the wave nature of light. But again, we digress just a bit. Let's just assume that light, for our purposes, is a wave for this discussion. And on figure 3.9, it talks about some important aspects. They identify the peaks up here as crests, and every one of the tops of the waveform are known as crests. So here's the first crest, the second crest. We would assume that there were crests prior to this. Like this comes from ... and at the other end of this, it continues on. So it's a continuous waveform. I'm just choosing a little segment of it. So if this were a line, this is a line segment that I'm looking at. This segment has crests. It also has troughs. Troughs are the low points. There would be another trough over here and another trough that we're just about reaching over here. So troughs are the low, crests are the high. The distance between crest to crest or trough to trough, whichever way you look at it, is the wavelength. So between these points, if there's a crest and there's a crest, there's the wavelength. Now wavelengths use the symbol lambda as their abbreviation, lowercase lambda. That is the same distance as the distance from trough to trough. Let's suppose that we had another one here. We had a second trough. The distance between trough to trough is also the wavelength. And the wavelength on this waveform, this distance is going to equal this distance. They're the same. Because this is an identical symmetric repeating form. So if we knew exactly where, let's say that this is the midway point between high and low, and you see it's not perfect because this distance here, if it was a perfect form, would be the same as this distance here. But if we knew the exact point of, let's say we're across the middle point here, from this point here where the form is coming up to this point here where the form is coming up, guess what that distance is? It's the wavelength. So if you find an identical portion on this form between one form and its repeating form, the distance between those points is one wavelength. If I had a yardstick here and I was able to measure this distance here, and if this were a perfectly drawn form, I could put one end on this form, the other end on this form, and as I traced it, they would perfectly trace each other as they move from, in this case, we're saying left to right. And the distance would be, in every place, one wavelength. So wavelength is the distance between, we define it as crest to crest or trough to trough, but it is actually every symmetric point on the waveform. That's one wavelength. I referred to these distances here, these amplitudes, abbreviated with capital A's. Amplitudes. They also would be exactly the same distance. It's not to scale here, it's a bad image, but this distance from midpoint to top to crest, and the distance from midpoint to trough, the low point, would be the same distance, referred to as the amplitude. Book definitions: the wavelength, the distance between crests or troughs of a wave, and amplitude, a measure of the height of the crests or the depths of the troughs of a wave. Okay? So amplitudes, those are the same. Those would be the same identical distances. Wavelengths, those would be the same identical distances throughout that waveform. At the bottom of page 99, they start talking about this aspect of color. And what does it mean we see light that's different colors? Hopefully you recognize that light that in a light wavelength, or a light form, a light wave, the color that we see corresponds to the wavelength of that light. Now, you may have thought of it in terms of frequency, you know, that the frequency of light, but we're going to find out very quickly that frequency and wavelength are related, that the frequency is equal to the speed of light divided by the wavelength. Okay? So, you can refer to this based upon its wavelength, but because we know the speed of light, you can also refer to it as the frequency. We're going to use wavelength now as our basis of discussion, but you could just as easily convert wavelengths into frequencies because we know the speed of light. But when you see light, we consider light, we know that the light, for example, in this room, appears to us to be virtually white. It's not truly white. Have you noticed in different light sources that the color of light that you actually see can be slightly different? I mean, we're experiencing that in my house because I'm reading all kinds of books and highlighting all kinds of stuff, and I've got some books where it's mostly highlighted and a few words are not highlighted, you know, one of those kind of deals with my doctoral studies. But as I'm going through and making all these highlights, I realize sometimes in our basement when I'm down there reading that even though all the overhead recessed lights are on, I open up the book and I can't see any highlighting. I know I've just marked this book up like crazy, and yet when I sit down, there's nothing on it. Why is that? Because the frequency of the light in that space is not the same, so that it doesn't make the yellow on the page pop out for me. And so I have to bring, actually with all these lights on, lots of lights, okay? We got a huge electric bill, but there's lots of lights on in the basement, and I have to bring a supplemental light down there, an LED high intensity light, a reading light, in order to see those things that I've highlighted. Because part of the optical deal is that certain wavelengths and certain frequencies cause certain things to, I'll say, pop, okay? But the original discussion on that is that some lights, or maybe you notice this when you take pictures, some lights have a bluer cast, some lights have a yellow cast. If you use an incandescent light versus a fluorescent light, I mean, I would say ladies, but guys maybe too, but you know you have a certain light that you put makeup on, right? Because you can sit down in front, okay, Ray, no confessions here. No confessions, this isn't a confession. But you sit down to do your makeup, right? What do you normally look for? Isn't it the natural light? Unless you know that you're going to be in a certain environment. And they do have those vanities, probably appropriate name, right? But those makeup lights where you can dial in to where you're going to be. Are you going to be outside? Are you going to be inside under fluorescent? Are you going to be inside under tungsten? Are you know, where are you going to be? Because what you'll do is you'll set your makeup with the appropriate light that you're going to be under because you want to appear a certain way under that light. That's because different lights cast different colors. And by casting different colors, they draw out different colors. So you're going to actually, and this is something, again, we used to live in Southern California, that it's a whole different mindset out there, but you can tell when a person is not in the light that they were designed for. That's why a lot of actresses and actors there too don't look right when you see them in public after they've been doing a shoot, because their makeup is set for a certain intensity and frequency of light, which is not natural light. So just as it's difficult to look like you've got no makeup on when you have makeup on, it's difficult to look like you have no makeup on with a high intensity, particular frequency light. And when you step away from that light, it's obvious that you've got tons of makeup on. Okay. All that to say that light that we see is based upon a combination, that we actually see is based upon a combination of multiple frequencies of light energy. And we're even going to say for a moment now that we're not going to consider light to just be visible. Because what we're really talking about is the electromagnetic spectrum. Frequencies of energy, some of which we identify as light because it fits within the range that our optical sensors can see, what we can see through these sensors. Certain frequencies of energy we hear. Certain frequencies of energy we see. Certain frequencies of energy we feel. I mean, you know when you step outside, it could be the same exact temperature inside or outside the building. Same temperature. But when you step out, if there's no breeze and you step into the sunlight, it feels warmer. Right? There's energy we're feeling because it's being delivered by light in a particular way. So when we see something that we might call a white light, And if you go to Lowe's or Home Depot and look at the light bulb section, you get to choose your color cast that you want, what frequency of light you want to be dominant. But a white light is actually a combination of all colors. When you have what we would call a purely white light, there is no such thing as white light. White is a combination of all different frequencies of light. And light is primarily known not for what it presents, but for what it excludes. If you notice on page 100, there is our rainbow of colors. And they represent those frequencies of light, those energies that we see as light, that we can visualize as light, moving from left to right. Notice the visible spectrum starts over here on the left side with red at 700 nanometers. Remember, nanometer is times 10 to the negative ninth. So 700 times 10 to the negative ninth meters is the wavelength for the left-hand side of the spectrum. 700 nanometers. And then all the way on the right-hand side, all the way over to violet, 400 nanometers. So it is getting smaller. You see, if you go from left to right, from 700 nanometers, 700 times 10 to the negative ninth meters, then all the way over to violet, 400 times 10 to the negative ninth meters, or 400 nanometers. But it's incredibly, incredibly small. The distance from crest to crest and trough to trough is very, very small. Now, they do make the point at the bottom of 100 that you don't need to memorize all the wavelengths. You don't have to memorize that 700 to 650 is red, and then we get to what we kind of call orange, and then we get to kind of what we call yellow, and then we get to what we kind of call green, and move all the way across. But you are expected to know Roygbiv. And you should have had that in our class already at this point. If you haven't, Roygbiv is just a way of remembering the colors from left to right. Roygbiv. Red, orange, yellow, green, blue, indigo, violet. Roygbiv. And so this is the this is the 400 nanometer range, and this is the 700 nanometer range. And so you should be able to say, I had a blue light, and then I have a yellow light. Which one has a larger wavelength? Right, so you should be able to say within Roygbiv, okay, I'm going from blue to yellow. My wavelength has increased. So get some kind of a relative understanding there. If you need specific numbers, they'll be given to you. Okay, but this concept of violet has a shorter wavelength than red, which has a longer wavelength, and they move in this direction from large to small wavelength, from red to violet, according to Roygbiv. Just pretend it's somebody's name. Now, one of the other things about light, and again, when I say science has determined, just as Tyler told us on the video, as everything should always have this disclaimer over it, okay? As best we understand now. Okay. I think we need to be very humble about this and say we don't absolutely know, really we don't absolutely know anything. Okay, but what we're talking about now is what is the best solutions that we have for certain things. And one of the things that we're going to present here is the concept that light has a speed which is constant, the speed of light. Speed of light, we're going to say is 3.0 times 10 to the 8th meters per second. 3.8 meters per second, that works out to be, 9.8 times 10 to, I don't use the English very much, so 9.8 times 10 to the 8 feet per second. Yep. Feet per second. And you can see in that third paragraph on page 101, that comes out to be 190,000 miles per hour. Oh, yeah. No, I was wrong. So easy to write MPH. It's miles per second. 190,000 miles per second. Even that won't get you a ticket in Louisville. Sorry, I had to figure out a driving joke in there somewhere, right? 190,000 miles per second. It's interesting because they actually figured out this number using a stopwatch. I've seen that Bonanza episode. They used a stopwatch now. But anyway, 190,000 miles per second. It's incredible speed. It's something, it's difficult for us to wrap our minds around that. But when we start talking about the speed of light, we talk about a light year. A light year is the distance that light can travel in a year. If it's going 190,000 miles per second, how many miles would it cover in a year? And that's a light year, the distance. But this is a physical constant. On page 101, again, the definition of a physical constant, a measurable quantity in nature that does not change. And we're going to suggest that the speed of light does not change. The speed of light is 3.08 times 10 to the 8th meters per second, always, for our purposes in this course, okay? Which becomes important because of this formula I wrote over here. We start talking about frequency. Again, on page 101, frequency, the number of wave crests or troughs that pass a point each second. When I had that waveform on the board and it was going like this, think again of being out in the ocean. If you were able to stand in a spot, let's say you were standing on a rock or a pier or something, you're standing here looking at the water, and you had a straight line in the water, and these waves were moving past you, and you see the waves going by, the frequency is, if you were looking just at the, let's say we're just looking at the crests, and I have a line here. How many crests go past my line every second? That would be my frequency. The frequency is, let's say that you hear, that's the way it looks for a wave. Let's say we're talking about music. Or let's make it even simpler, my hand clapping. How many hand claps do you hear every second? That's the frequency. Hopefully you understand the concept of when I go. I've now increased the frequency. What have I increased? I've increased how many times you hear a hand clap every second. Now, if you were to visualize that, let's say the waveform, as the waveform's going by, okay? So you have like an oscilloscope, it's going, showing you the waveform. If you could hear my hand, you would see a certain, every time you hear a clap, let's say that that's a crest. So as you're seeing this go by, this kind of a waveform, we have a nice gentle peak, peak, peak. As I increase the tempo, you would see more waveforms. It would transition something like this. Here's our base. Let's say we have a waveform that looks like this. But then, as I start clapping faster, it starts to more go by every second. So what the effect of the visualization is that this wavelength now is coming closer. The peaks are happening, that's cute, peaks are happening more often, every second. For that, what that looks like is here. If I go to the place where I'm clapping really fast, okay, we're talking about a waveform that's very, very tight like that. So from a very slow to an increase to very rapidly. And on our waveform here, we could divide this up, and let's say that from here to here, this is one, it's not only one wavelength, but it's also 1 second. Well, if I have one wavelength for every 1 second, my frequency is 1 hertz. A hertz is a cycle per second. I have 1 cycle for every second. If I double the speed at which you're hearing, if I double its tempo, then I would actually have, whereas I have 1 crest here, if I double the frequency, that means I have to have 2 crests, right? And for 2 crests, now my wavelength here is 1/2 the distance of this one. So I get twice as many, but each one of them are closer together. I have 2 times as many, but their distance between them is greater. Now see what's happening here. As my wavelength is getting shorter, my frequency is getting higher more often. Over here, I have, maybe we double that. So rather than 1 and 2, let's say that we have 4. Well, there's 1, 2, 3, 4. See, in this case here, my wavelength is half again. But for every second, each one of these between the lines represents a second. So here's a second, here's a second, and here's a second. I've got half the wavelength but double the frequency. And then again, half the wavelength again but double the frequency. Notice that wavelength and frequency are inversely related. What does that mean? We get that from this formula over here. You're going to need to use this formula. Frequency is equal to the speed of light divided by the wavelength. Frequency is equal to the speed of light divided by the wavelength, excuse me. So, for example, if we want to know the frequency of this 700 nanometer wave, the speed of light is 3.0 times 10 to the 8th meters per second. We're going to divide that by, over here, the wavelength. Let's say we have a 700 nanometer wavelength. It looks to us to be red. Its frequency then would be, this would be all be divided by 700 times 10 to the negative 9th meters. When we do that math, and I don't have it in front of me here, but actually if you look over on page 103, example 3.2, they work through a problem. So rather than me just throwing one up there, let's look at what they've done on 3.2. They said a violet light wave, not violent, violet, okay? A violet light wave has a wavelength of 405 nanometers. Now that doesn't mean that every violet light has that wavelength. It means that this particular light, which we can see and to us appears to be violet, this one in particular happens to have a 405 nanometer wavelength. What is its frequency? And you notice that they tell you in the book that C equals 3.0 times 10 to the 8th meters per second, and that the prefix nano means 10 to the negative 9th. So you should be able to work the problem from there. We'll skip down to the middle of the page there. You notice where it says frequency is equal to the speed of light. In this case, I used 3.08 times 10 to the 8th, just like they did. And then below that, they're looking at a 4.05 times 10 to the negative 7th meter, whereas we were looking at the 700 times 10 to the negative 9th meter. But in either case, the frequency, excuse me, the speed of light, which is a constant, always, always, always the same, divided by whatever the wavelength of that particular light you're looking at or considering. You do the math there and you get a frequency. The frequency here, for example, they have 7.4 times 10 to the 4th 1 per seconds. Okay? 1 per seconds. How do they come up with a unit known as 1 per seconds? Have you ever heard of a 1 per second before? Give me 17 1 per seconds. Okay. Well, look at the units of my math. It's a derived unit. It's a unit which in and of itself we may never have come up with or used or seen, but because the math draws us to a certain mathematical number, it also draws us to a certain unit. So in this case, just looking at the units, I have meters per second divided by meters. I can always make something a fraction, right? I can put it over 1. And then, if you have trouble with this math, remember that to divide something is the same as multiplying by its reciprocal. So if I were to do that here, if I were to go meters per second times the reciprocal of this, this would be 1 over meters. And now look what happens to meters. Meters cancels meters, so those are both 1s, and the units become 1 per second. So in the case here of this 405 nanometer wavelength, that corresponds to a 7.4 times 10 to the fourth 1 per second. Now, we have a common name for a 1 per second, and we use the name of hertz. Hertz. Hertz is a common name for a unit that is mathematically a 1 per second. So when I say that a certain wavelength is going past me at 70 hertz, what that means is it's going past me with a frequency of 70 waveforms per second. 70 hertz. So a hertz is a 1 per second. That's the name for that unit. Okay. A hertz is a 1 per second. We can also notice here a point that they make on page 104. And again, not only do I encourage you to, I expect that you're reading the book, so what I'm doing here is giving you significant highlights from the portions you either have or will read, right? But they make this statement in the middle of page 104 that when the wavelength is large, the frequency is small, and when the wavelength is small, the frequency is large. Now, you should be able to see that indirect relationship here from this formula. Whenever frequency is equal to, now this is a constant, right? It doesn't change. One way that I could rearrange this formula then, let's put it in with regard to the speed of light. A constant speed of light is equal to the frequency times the wavelength. Do you see that? I've rearranged this formula, frequency equals speed of light divided by wavelength. I've rearranged it to solve for the speed of light. The speed of light is equal to the frequency times the wavelength. And so frequency and wavelength, whatever it is, whatever they are at any particular point for a certain waveform, the product of their multiplication here has to equal a constant. What does that mean practically speaking? If I take the frequency of a wave and I cut it in half, what has to happen? If frequency is cut in half, what happens to wavelength? Pardon? No, if this is cut in half, let's use a practical example. Let's say 12 equals 3 times 4. Okay? But let's say that I now say, okay, rather than 4, I've got 2. But I still need to come up with a constant of 12. So what about this number here? What does it have to be? Has to be 6, right? Here's what's happening. If I have a certain formula that gives me a number, and I change one component of that formula, but I still have to get the same number, I'm not going to change the speed of light. So in this example, if I need 12, and I get 12 by doing 3 times 4, if I cut one of them in half, what has just happened to the other number? I've doubled it, right? If I have one, I have to double the other to get the same number. And since we're talking about over here the speed of light, it doesn't change. So anything that happens to the frequency, the inverse has to happen to the wavelength. If I cut the frequency in half, the wavelength has to be double. If I cut the wavelength in half, the frequency has to be double. If I cut the frequency in a third, the wavelength has to be multiplied by 3, the reciprocal. If I cut the frequency by 6, if I take 1/6 of the frequency, what must the wavelength be? 6 times as much. They're indirectly related in the sense that as one goes down, the other one has to go up. And they have to go up in proportion so that the product of their multiplication has to equal 3.0 times 10 to the 8th meters per second. That's what it means for wavelength and frequency to interact with light's physical constant speed of 3.0 times 10 to the 8th meters per second. And so lastly, just looking at the top of page 105, looking at the electromagnetic spectrum, this is what I was saying earlier. Notice the wavelengths that are depicted on figure 311, okay? The wavelengths that go from left to right. In that diagram there is a segment of the visible spectrum. You see where the rainbow is? Just between the ultraviolet and the infrared. See that? There's the rainbow. That rainbow is our Roygbiv, which on the couple pages previous we had the rainbow, which we see with our eyes. But the point they're making is that in the overall electromagnetic spectrum, the visible light is only a portion of the electromagnetic spectrum. It's that only that portion that we can see with our eyes. You've got started way over on the left with a very, 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 very small wavelength. Since it has a very, very, very small wavelength, it must have what kind of a frequency? Very large frequency. Good, Ray. They're inversely related. So if you have a very small wavelength, notice on top it gives you the wavelength, on the bottom it gives you the frequency. So a very, very small wavelength has a very, very large frequency. On the right-hand side, it has a relatively small, has a relatively large wavelength at 10 to the second meters, but below that, it has a very small frequency. And we'll pick it up there with figure 311 tomorrow.